Hello everyone, my name is John Onwemeka. I'm a student at McGill University. My supervisors are Yajin Liu and Rebecca Harriet. And my talk today is on our study on the relationship between earthquake p-values and differential stress in the Shaliver seismic zone Eastern Canada. Faults slip in a variety of styles that reflect the relative magnitude of the orthogonal principal stresses acting on the region. That is one vertical and two horizontal stresses. We get normal faulting if the vertical stress is the largest, stress faulting if the vertical stress is the intermediate, and reverse thrust or thrust faulting if the vertical stress is the smallest. These stresses are clearly paramount in understanding of earthquake processes. At shallow depths, the magnitude of these stresses are commonly measured in situ, for example, with borehole breakouts. However, at greater depths, in situ measurements are impractical, so indirect methods such as stress inversion with focal mechanism data are used to estimate the relative magnitude. Earthquake size distribution, for the most part, follows a power law. The slope of this power law describes the relative occurrence of small and large events and is referred to as the B value. Low B values indicate a larger proportion of larger events, whereas a high B value indicates a larger proportion of smaller events. Given that seismic activities are governed by fault strength and prevailing stresses, an important question is raised on what the frequency magnitude distribution can tell us about stress condition. Several researchers have studied the relationship between B value and physical mechanism. For example, Scholler et al. In their 2005 paper found a systematic dependence of B values on earthquake focal mechanism where thrust, strike slip, and normal faulting events have smaller, intermediate, and larger B values respectively. Mori and Abercrombie in 1997 found that B values decrease linearly with depth and interpreted their observation as a B value dependence on material heterogeneity. Some others, for example, Scholes in 2015 found that B values inversely correlates with differential stress. This relationship is supported by laboratory experiments and we explore it in this study. In order to further explore the dependence of B value on differential stress, we must first determine the magnitude of the principal stresses, or at least a representation of their relative magnitude. R is a representation of the relative magnitude of the three principal stresses, and it can be determined from stress inversion. R decreases with decrease in the difference between the maximum and intermediate stress and or increase in the difference between the maximum and minimum stresses. The denominator of R is the differential stress magnitude. For optimally oriented brittle faults, Zuback and Townend in 2001 determined a theoretical relationship that indicates differential stress increases with depth. This relationship is supported by field observation. For instance, in the Canadian Shield, empirical relationship from field observation indicate a linear relationship between differential stress and depth. Therefore, in this study, we use R as a proxy for differential stress and probe how R values relate with B value. A little bit of introduction of our study area. The Chaliver seismic zone is located in eastern Canada within the St. Lawrence Paleoreef system. The pre-existing normal faults are overprinted by a late Ordovician to early Silurian meteorite impact measuring almost 60 km in diameter. About 180 earthquakes are reported every year in the region, and the figure on the left shows the almost 6,000 earthquakes reported in the Chaliver seismic zone between January of 1985 to May of 2020. So our objective in this study is to, one, determine how B value is distributed in the Chaliver seismic zone. Second, determine the orientation of the principal stresses and the stress ratios in the area. And lastly, explore the possibility of a relationship between B value and stress ratio. So let's explore the first objective. To calculate the B values, we use relocated seismicity of Yu et al. 2016 and Onwemeka et al. 2018. The seismicity in the Chaliver region is diffuse, so we use a probabilistic clustering technique to divide the region into spatial clusters and calculate B value for each cluster. This figure shows the map view of the 3D spatial clustering. We estimate the B value with the maximum likelihood method. Each cluster represent grouping of events that are spatially connected and share common characteristics. The color-coded numbers represent B-value of the respective cluster. We make profiles to more clearly show the spatial distribution of the events and the clusters. When you look at the map view, you would immediately notice overlaps in the clusters, but from the cross sections, it becomes more clearer that the clusters are spatially connected but distinct. In these figures, there are two families of clusters. One for earthquakes within the upper 18 kilometers, that is the red and yellow clusters. Another for the deeper earthquakes, that's the blue and green clusters. Majority of the events in the Shaliver seismic zone occur within the upper 18 kilometers and within the impact structure. So these clusters highlight what might be interpreted as somewhat differing physical condition, for example, dense fracture network within the upper 18 kilometers. The average B value in the upper cluster is 0.8. In the lower cluster, the average B value is 0.7, slightly lower than in the upper cluster. This decrease of B value with depth is in agreement with the previous studies. Next, we investigate stress ratios and orientations of the principal stresses within these clusters. As I mentioned earlier, in situ stress measurements are impractical for greater depths, that is middle, cross, and deeper. So we use focal mechanism solutions to invert for stress ratios and orientations. We calculated 161 focal mechanisms for events of magnitude 1.3 and above. We augment our dataset with focal mechanism data from Mazzotti and Townley in 2010. The figure on the left is a map view of the focal mechanism solutions color-coded by clusters. On the right, we show the distribution of the faulting style in each cluster. This faulting style distribution plot shows that the events are predominantly thrust faulting events. Next, we use our MSATC as the MATLAB version of SATC stress inversion code of Heidelberg and Michael 2006, written by Martinez, Gazon, and her colleagues for the stress inversion. Here we show the stress inversion results. These are busy figures, but I'll explain everything in detail. In the figure on the left, the black converging arrows show the azimuth and mode of the regional stress inferred from in situ measurements within the upper 2 kilometers. The orientation of the three principal stresses, blue for the minimum, green for the intermediate, and red for the maximum principal stress respectively, is shown in the stereo-net. The color-coded numbers indicate the azimuth of the maximum principal stress within the respective clusters. On the right, the stereo-nets are plotted on the cross sections. The results show that the maximum principal stress in the Shaliver seismic zone is rotated clockwise from the regional stress direction. The eastward rotation of the maximum principal stress is more in the lower cluster relative to the upper clusters. The stress rotation suggests that the source of stress perturbation is different from the regional stress, or the larger proportion of the stress perturbation in the Shaliver seismic zone is from sources different from the regional stress. In this figure on the left, we show the orientation of the maximum horizontal stress in each of the clusters, and on the right we show a figure from Tyrone et al. 2018. The authors in that paper looked at GPS trend rate variation in the St. Lawrence River. Broadly, the GPS horizontal velocities show similar trend of rotation from the regional stress. The deformation recorded by the GPS is suggested to be from glacial isostatic adjustment. Now, let's take a closer look at the GPS horizontal velocity fields in the Shaliver area that's within this red box. From this close-up view, we see strong local variation, but most of the horizontal velocities reflect a consistent eastwards rotation from the regional stress direction. The GPS horizontal velocity fields show deformation primarily driven by postglacial isostatic adjustment. This is another source of evidence that shows that deformation in the Shaliver seismic zone is dominated by physical mechanisms different from the mechanisms that sway the trend of the regional stress. Next, we put all this information together to establish a relationship between the differential stress and b-values in the Shalev assessment zone. Now, the existence of such relationship would suggest that b-values could serve as stress proxy for the Shalev assessment zone. This figure here shows the relationship between b-value and R, which serves as a proxy for differential stress. These observations are few, however, they show an inverse relationship between b-value and differential stress, which makes the case for the use of b-value as a stress meter proxy. These results agree with several other studies on this subject, including laboratory studies and field observations for a variety of tectonic settings. In conclusion, we find that b-values in the CSZ, in the Shalev seismic zone, are consistent with expected values for tectonic earthquake, that is, they are close to 1, and they decrease with depth. The maximum principal stress is oriented roughly east-west all across the Shalev seismic zone, hence facilitates reverse sense reactivation of the northeast-southwest trending normal faults. Finally, b-value linearly correlates with stress ratio, indicating an inverse correlation with differential stress, suggesting a potential for use as a stress meter proxy in the Shalev seismic zone. Thank you.